is my topic. It's not explicitly about how to do interface management. What it is more to do with is what has led to the situation where interface definition and management is done quite so badly. Okay. In my industrial background, I was like project engineering manager and head of systems engineering at a particular division of Thales for nearly 30 years, and head of a group of project design engineers and integration engineers. And I got fed up with the continual stream of failures in integration where one end, another end, or the functionality distribution between two system components fail to work in integration testing. And it's always down to interface definition, interface implementation, and sometimes the preliminary testing before submitting to a system integration lab. So when I started berating the engineers involved, well, they all retorted with, well, we don't know how to do it. There's nothing in the literature and there's no training courses out there. And I thought, that can't be right. Surely that can't be right. But I did some digging and found out that, in fact, yes, it was right. There was very little documented out there in the literature and no training courses. So I developed a training course initially internally to Thales, and with a bit of help from Ian Pressland, then opened it out to Incosi UK with the aid of Hazel Woodcock. And then I turned it into this little book, the Don't Panic Guide that Ian talked about, which does cover a certain amount of best practice in interface engineering that I've come across. But the theme of this presentation is about why there are blind spots in engineering literature and engineering practice in interface management, and potentially how we might challenge the standard of practice out there. Okay, so part of that is challenging the perception of an engineer who ignores the world outside this system element. I am sure you have all come across engineers who say, I just want to design my bit and not worry about anybody else. I don't want to know about the outside world. I just want to design the function and performance of the bit that I'm responsible for, which is completely useless if that system element that they're responsible for is part of a larger system and has to interact with it. The second objective is to remove the excuse that there's no training or guidance in interfaces, because now there is. And also to challenge the way that architecting has been done historically and is still very much in current practice, to left shift to earlier in the architecting process the consideration of interfaces. And I'm going to cover, first of all, what's in the literature currently, then a little diversion about the somebody else's problem field, cover some elements of best practice, but not in great detail. If you want the detail, I suggest you look in the book, or there is a bit more. There is a paper that accompanies this presentation that was presented at the Incosi Annual Systems Engineering Conference in 2019. And if you look online on the Incosi website, you can probably find it quite easily. Then to talk about left shifting, an example to say this is not a universal recipe. There will still be some common problems that you encounter, and a quick talk about what types of problems they are. And finally, about life cycle considerations. And then we can conclude and you can ask me some questions. However, The way this presentation is constructed, I will be using very few words and bullet point lists. I'm trying to use pictures as much as possible to put those mental images in place. If you want the supporting words and pictures, then yes, get the paper, get the book. All right, so what's in the literature? It's a little bit of a history lesson. If we look at one of the very earliest standards on systems engineering, this is IEEE 1220, which is was actually first published a very long time ago, but the most recent version I think is 2005. So on its page 3, it starts with a picture of a system breakdown structure without covering interfaces at all. And the way it proceeds is to say only to cover a waterfall life cycle. You do requirements first, then architecting, then or logical design, then physical design, and then implementation. And it treats the definition of interfaces as a bit of a tail end Charlie to each of those steps. So do your functional performance requirements first, then think a little bit about interfaces. Do your architecting first, then think a little bit about interfaces, with no feedback loops and no participation of the consideration of interfaces in your requirements and architecting decisions. Right. Then we moved on to a slightly better standard, EIA 632, which came somewhat later. This has a grand total of 7 lines on interfaces, and it has a summary table of how to do decomposition from requirements and system breakdown structures, which is an exact copy of the one in IEEE 1220, so it doesn't particularly add value in that respect. Moving on, there are some useful NASA and NIST, and I can't remember what that stands for, standards. So here we have an example here, NASA reference publication 1370, training manual for elements of interface definition and control, which aren't bad as long as your interfaces are all about software and communication systems. If they're hardware interfaces, electronic interfaces, mechanical interfaces, or contact interfaces, no use whatsoever. It also tells you a fair bit about what should be in your interface definition, but with no consideration of the process that you might use to get to the right answers. All right. Okay, now we come on to the Systems Engineering Handbook. I've got a picture of version 4 here. Version 5, or 5th edition, has just been released, and I haven't had a chance to check it yet. There is some quite good words about interface definition in section 4.4 on architecture definition, and then again in one of the things on cross-cutting processes, back in chapter 9, I think it is, might be chapter 10, which it considers a basic form of interaction mapping, which it calls coupling matrices, which is very old wording based on a book by Jeff Grady that was about 30 years old, and I'll come on to in a minute. We might know it as n-squared charts, or occasionally design structure matrices nowadays. It's good, but in terms of a whole system life cycle, there is no end-to-end time-based story about how to do the interfaces themselves. So, as I said, the systems engineering body of knowledge, again, is better still, but again, there's no end-to-end story. Then I said about the book by Jeff Grady. As I say, it's at least 30 years old. It's way out of print, and second-hand copies are changing hands for about $300 on eBay, which is quite astonishing. And then there's a little bit by Hilary Sillitoe in his book on architecting systems, which is a recommended read anyway, but it again is not covering the treatment of interfaces front and center in architecting. So that's the history lesson. Now I want to talk about somebody else's problem field. Now, on the right, these are all Cambridge University alumni. On the right is a hypothetical depiction of there being a pink rhinoceros in the room. And there was a legendary debate between Ludwig von Wittgenstein, author of Tractatus Logico-Philosophico, and Bertrand Russell, author of The History and Philosophy of Western Science, which is in principle all about the debate between empiricism and existentialism, where one of them tried to argue that just because you couldn't see a pink rhinoceros in the room, that didn't mean it wasn't there. Where the other one was saying, well, the evidence leads you to suggest or to conclude reasonably comfortably that it's not there. However, it all depends on your point of view. And interfaces are very much like that. If you are considering your top-down architecting into terms of its functional components, it is very easy to overlook the interfaces. They're like the pink rhinoceroses. They're there even if you don't recognize them. They're implicit. Guy on the left is, of course, Douglas Adams, author of The Hitchhiker's Guide to the Galaxy, which is a far more easily digestible description of the same problem. In fact, he called it the somebody else's problem field, which he defined as something we can't see or don't see, or our brain doesn't let us see because we think it's somebody else's problem. The brain just edits it out. It's like a blind spot. And that's exactly what interfaces do if they are not made the responsibility of somebody to think about. All right, so let's have a look at two models of how we represent systems at top level. So the first one is, it comes from a very famous paper by James Martin called The Seven Samurai of Systems Engineering, where he starts with the idea of a context system or system context, which is a mapping of the problem space and the set of interacting systems into which we are going to have to introduce a new one or a modified one. And every system that is introduced is intended to counter a particular problem or a gap in the context system space. And eventually, what you would like to end up with is a deployed system, which we'll call S4, which collaborates with other systems, S5, in what we see as a modified context system, because every time you introduce a system into a space, it alters the behavior of both systems. All right, and that in itself may cause some new problems, P2. But along the way, the problem may be being caused by a competing system, and the competing system is still going to compete with our deployed system, so that's S7. But also, we don't magically get from a piece of paper to a deployed system, S4. We have to envisage an intervention system, S2, which starts from the blank sheet of paper and creates the deployed system, which is part of a realization system, your enterprise, for example, which has sets of processes, documentation structures, design tools, etc., in order to realize and turn that blank sheet of paper via the intervention system into the deployed system. And once you've delivered it, you have to keep it going. So we've got a sustainment system, S6. But we have also got an influence diagram here and a map of what interacts with what and for what purpose. Now let's compare that with the typical means of representation of a system, because generally speaking, when an engineer is faced with that problem P1, that's not what they do. That's not their mental map of what's going on. Typically, an engineer will leap to the first solution that he can think of and create a system breakdown structure. So on the right, we have the SBS, our system breakdown structure. It says, okay, to combat this need of needing aircraft not to run into each other, let's have an air traffic control system. What do we need for that? We need some radars, we need a control tower, we need a whole load of infrastructure services, we need some enabling systems to make it happen. All right, and then below that, we will decompose and decompose and decompose. Now, what we have done by that process is that we have removed all visibility of any interfaces. You now cannot see from an SBS any interaction between the air traffic control system and the aircraft, the general public, competition in the electromagnetic spectrum, interaction with military forces or emergency services, for example. And you can't see the interactions between the component system elements, like between the surveillance radar, the precision approach radar. Do they talk to each other? Do they interfere with each other? You cannot tell from a system breakdown structure picture. So why does that matter? Okay, it matters for several reasons. First of all, we can allocate responsibility for implementing each system element to a team, or in some cases an individual design engineer, but there will be interfaces between them, whether they are made explicit or whether they remain implicit. So let us suppose you have to define and implement an interface that enables interaction in a controlled manner. That interface has two ends, at least two ends. And if the design engineers involved don't design their end of the system with a common interface in mind, then we get this Mexican standoff, because each designer or team will say, well, okay, my end of the interface doesn't look like that, you've got to change. And the second end will say, well, why should I change? You change. And in general, changing the design to meet the interfaces costs money and nobody wants to pay for it. So definitely needs doing in advance. The other reason is decomposition explosion. So let's suppose that our system is composed of 5 system elements, all of which talk to each other. That's potentially 10 internal interfaces, 20 if the interface is not symmetrical, and more if you've got different interfaces for software, electronics, mechanical, etc. Now let's suppose that our system talks to 5 different external systems. Okay, so even if we make one, let's call it a concentrator node, responsible for managing the communication with the external systems, that's an additional 5 interfaces. If we don't design with that in mind, it could be that all of our 5 internal system elements talk to all 5 of the external systems, which adds another 25 interfaces. And in general, the deeper the hierarchy of your system architecture, the faster that number of interfaces multiplies. It typically goes down, goes up with the square of the number of components as you go down each level. All right, which with careful design, we can reduce to about 2n. All right, The other thing is about traceability, in that we now have to develop a set of requirements for our interfaces and map our system element requirements at lower levels, both of them, to the requirements, the design and the implementation of the interfaces connecting them. So you very quickly get into the problem that you have to manage three-way traceability for a very deep hierarchy. All right, and then we add testing as well, which makes it even more complicated. Excuse me, I've got a bit of a sore throat. Okay, next thing to say is that it's not just software. Here's an example from overhead line electrification from railway systems. So we have electric current being passed from the overhead line via a pantographic arm to the onboard train systems. So the intended interaction, that the interface that you design for, is electrical voltage and current, and of course there may be transients on that. But there will also be time varying forces vertically, depending on the tension in the overhead line and the elasticity of the pantograph arm, longitudinal forces due to friction, which transfer heat. There can be flash arcing when the pantograph arm does not maintain contact with the line. There will certainly be a big electromagnetic field flux, because that interface is moving at maybe 200 miles per hour. Vibrational forces, shock at the joints, and then mass transfer as well, moisture and salt deposition, carbon deposits, and so on. So all of those, excuse me, have to be captured, specified, and designed against by the designers at both ends. Right, so having set all that as the background, let's have a look at some best practices. The first one is what I call the separation principle, where we say we've got a notional plane of the interface. And what we try and do is separate in the specification what is passed across the interface, or the form of the interface, from the stimulus response behavior across the interface from system A and system B. And the purpose of that is so that everything is specified only in one place. So you don't have any functionality in an interface specification, and you don't have the details of the interface in the specification of the systems or system elements at each end. Trust me, you get a much cleaner configuration management process or change management process if you do it this way. Best practice 2 is drawing the context diagram. What's inside our system boundary? What is the things that it will interact with outside our system boundary, both intentionally and unintentionally? Then our numbered indexes around that circle is what is being exchanged, in what format, how often, etc. All right, so there's more on it in the book. Best practice 3 is drawing sequence diagrams for those interactions, not necessarily just software, any kind of mass, energy, or information exchanges across those nominal planes of each interface in logical sequences. Start with a black box model here, where you've only got one swim lane for your entire system, and then move on to white box models, where you break your system down into its constituent elements. Best practice 4 is using layered models as patterns. So here, this is the OSI, the open systems interconnection 7-layer model, much beloved by the communications and telecommunications industry. That's fine, but we can use that as a metaphor even if there's no software or comms in the interface. So for our pantograph example, we can say, actually, at the very top level, what we want to be able to do without necessarily specifying the details is consider only the power demand versus power supply. And perhaps think about load balancing at the same time. So at the top level, we would only put that in our top level interface specification. But we can use this OSI pattern to say, at each level, within each swim lane, we depend on services provided by layers below. So the load balancing, it depends on power switching, safety trips and wiring and connectors at the lowest levels, and try and make those vertical interfaces as standard as possible so that you don't need to rewrite them for every project. Then we can add the intermediate systems at a lower level for the overhead lines, pantograph arm itself, for example, and the cabling and the power bus. And that works, just as well for energy and mass transfer as it does for information. Best practice 5 is turning all of that into a black box n-squared chart. So we note it all down. What's the interface between our system and the outside world? First of all, at black box level. So we look at interfaces between our system and its users, perhaps different classes of users, with its physical environment or environments, and between our system and all of the external systems that it has to interact with. Right. Then best practice 6 is extending that to do white box n-squared chart, where we put a candidate decomposition of our system into its constituent elements, then look at the content of all of the interfaces between those system elements in the top left-hand corner, and also the mapping of how that works in implementing the system level interfaces to the outside world, implemented by our lower level system elements. All right, and then as far as possible, try and play with those architecting options and decompose our system in different ways such that we get as few entries as possible off the leading diagonal within our system in the top left, and only 1 or 2 rows and 1 or 2 columns out to the user's environments and external systems. And then my last best practice that I'm going to recommend, best practice 8, is saying, don't just do it once. Draw it from, where did we start from? What was our legacy system integration with the outside world and between the internal elements? Then where are we trying to get to, our deployed system? And it may have different states and modes, which we may want to represent separately. For example, if it's in a degraded operation mode, or surveillance mode, tracking mode, firing mode, or if it's in a built-in test mode or a maintenance mode, for example, what do the n-squared charts look like? Why do we do this? Because inevitably it will uncover new and undiscovered or uncaptured interfaces that we need to design for. But along the way, we're going to have intermediate configuration states, perhaps for internal testing purposes, perhaps for diagnostics purposes with test equipment. But more importantly, between our laboratory testing and being fully deployed, there may be things needed for installation, things needed for commissioning and validation testing, field trials, etc., which may define new interfaces again, which may not even be present in the final deployed system. Right. So one thing that I would quite like you to put in the chat box, people, either now or at the end, is that I've put together those eight best practices. How many of them do you use in your day jobs? And how many do you think you should use going forward? And don't just say 8 for that one, because it may be that some of those are not applicable to what you do. But I'm interested in the answers, because coming back to the purpose of the presentation, it's about where are the blind spots? Why are the blind spots there? All right, and I said I'd talk about left shifting in architecting. So this is what, at a very high level, the standards like IEEE 1220 and EIA 632 look like. So we do requirements, then architecting, then logical and functional design, then physical design, and we do the interface design at successive levels of analysis with no feedback. But where we need to get to is to say, yes, okay, in principle, that's true, but at each step, we need to think about, by using those best practice tools, our context diagrams, our n-squared charts, and our configuration states lifecycle, what new interfaces does that imply? If we have a candidate architecture, how complex does that make the interaction between our system elements and the outside world? How complex does that make it? Do we need to simplify? So we can deduce a set of interface constraints actually quite early on in our system lifecycle and feed that back and maybe challenge the requirements, or at the very least, challenge how we do our optimum architecture. Okay, so going back to my pantograph example again, in green I have the electrical voltage and current is the intended interaction. Left to their own devices, if you've got one set of people designing the train system and another set of people designing the overhead line supply system, you can probably rely on them to talk to each other, to put an envelope around what they expect the vertical forces to be, the longitudinal forces due to friction, and any heat transfer across the physical implementation of the interface. However, things like the flash arcing, the electromagnetic field flux, and in particular things like moisture and salt deposition, which might interrupt the electrical conductivity, rapidly become somebody else's problem. So the rolling stock manufacturers say, no, it's the overhead line maintainer's job to keep the surface of the cable free from moisture and rust. And the overhead line manufacturers may say, no, the rolling stock, the pantographic arm, should have a capability to clean the cable as it goes. But unless this is considered right up front and an agreement established about whose responsibility is to make that interface as clean as possible, it's not going to work. So the flows across the interface, not just software and comms, drive extra functional and non-functional requirements on the system elements at each end. All right. Yeah, okay, I'll give myself a couple of minutes here. There's no right answer to some of these. Here are 5 potential areas where there might not be a single right answer for the interfaces. And I will take built-in test as a particular example to say, are you going to have one central system element that understands all of the test signals needed by every other system element in the system? It generates those test signals, propagates them, waits for the tellbacks, and then interprets the outcome. Or, so that's a fairly centralized architecture. Or are you going to have a much thinner central system element, which says you're the expert on how to test yourself to each of its other system elements, generate suitable test signals, tell me whether you're working or not. Okay, so that's a more distributed architecture. Likewise, power, to say, am I going to supply mains voltage to every individual system element and it does its own down conversion, or am I going to have a dedicated power supply unit that distributes low voltage supplies to each system element, which gives a single point of failure? But you know, all of these architecting decisions need to be talked through for the minimal level of complexity, number of interfaces, and risk. Okay, so this is what the feedback looks like. We're going to have a trial decomposition into subsystems, and we're going to evaluate the effect on the interface decompositions in terms of organizational complexity, complexity of the implementation of the functionality across each interface, the number of interfaces, and the risk, development risk. And then think about, is that view of the implementability of the architecture okay? If it is, go on, generate the specification tree, both the system elements and the interfaces, and get on with it. And if it's not okay, you've got time to change your mind, change the architecture to make it simpler. Okay, one last thing today is the requirement from hell. System A shall interface to System B via bearer X, which is so easy to say. I'm sorry to say, I've seen that even from our own Ministry of Defence rather more often than I care to mention. That's fine, but what if the interface to System B is not published? The bearer X interface specification is not fully known. Bowman. And what are we going to do about it? And there is a little bit of a recipe in the book for that, but it is something to say, don't accept a requirement like that. It is tantamount to signing a blank check. All right. Okay. So I've looked at some gaps in the literature, started to overcome the lack of a life cycle oriented view of interface evolution. I've looked at those 8 key principles and some best practice methods, and I've tried to get across the consideration of interfaces in architecting, which necessarily should force engineers to look outside the box and think about how to do better and not just focus on their internal design to the exclusion of the outside world. And with that, I'm going to open it out to questions. Thank you all very much for listening.
Thank you, Paul. So you asked the audience a question about use of some of the techniques. There's been a few responses in the chat. It looks like context diagrams at n² appear to be gaining the most chat, if nothing else. Sometimes the chat is, I'd like to use n² if only I understood them better.
Mm-hmm. Yeah.
So some good stuff there. There's a few questions, a few observations, so I'll work through from the top and we'll see where we get to. So quite an early observation from Sanjeev Apichala concerns the work of Jens Rasmussen and whether you're familiar with his work around socio-technical approaches to systems.
Yeah, I've been having a conversation with him offline, as it happens. I didn't have time to cover it today, but in the book, I definitely recommend the idea of using context diagrams, not just for the representation of interactions between systems and systems elements, but also for the representation of interactions between organizations up and down the supply chain, between different OEMs and so on. Because the things that are being exchanged are different in that respect. Instead of mass energy and information, then typically what you get is specifications going one way across an organizational interface and change proposals and test evidence, for example, and then there's acceptance, resolutions, and money going the other ways. All right, so yes, draw the organization context diagrams, because one of the big residual problems is if your system context boundary does not align with the organizational context boundary. An example would be where you are responsible for providing X, but you don't have control over the supply of some part of X. It's mandated by your customer or one of your fund holding stakeholders. Okay, does that answer the question?
Okay, so next question I have is from Jagdeep Singh. So the question is there criteria we can use when selecting the lead interface? So we have two systems that have an interface between them. Is there a particular process you go through, I guess, for deciding which system was taking the lead, which was subservient
Yes.
or whatever?
If one organization is provably more of a domain expert than the other, then they should probably take the lead. But in a system of systems, there may be no overall owner, in which case everything has to be done by negotiation. There is no lead. If it is a Ministry of Defence-led procurement, then I'm afraid, and the MOD don't like this, as prime system integrator, they have to accept responsibility for brokering the negotiation between the two contractors. Yeah, and again, they may designate one of them as a lead, or the MOD may, and Ian has personal experience of this, designate a third-party system, prime system integrator, to moderate the discussion between the two contractors.
So, Paul, I think the next question was, so the best example of failure of interface failure is the Crossrail project in 2018. How the method advanced here can address the Crossrail type of problem. Do you agree?
I think I need Sanjeev to explain what the problem was. That's after I left Network Rail.
Okay, that's fine. I'll carry on with the questions, and if it pops up in the chat, I'll let you know.
Okay.
So TSIs specify these interfaces in the railway context. Why do we need other interface specification for pantograph?
That's fine if the specification is complete. Typically they're not. And the other reason is about the generic nature of standards. Typically, this is particularly true of telecom standards and wiring standards. The standards are the lowest common denominator of the set of things that all interested parties can agree on. And there are elements which are left unresolved or underspecified, which are subject to either options or needing a specific example. Or if you have a very wide voltage tolerance or current tolerance, you might specifically want to narrow that down for a particular project. So what you would then use is something like an interface definition document, which says we're using this particular TSI, but with this range, or we're using this particular environmental performance standard, but for this temperature range, this humidity range, this air pressure range.
Perfect, thank you. And the next one, which would be the best technique to determine whether systems are tightly coupled / interdependent or not?
going to answer another one from Sanjeev at the same time about the use of n-squared charts. If you draw your n-squared chart between your system elements, and they can be used to think about all of the things that might become emergent properties, unintended coupling between system elements, and then you can cater for them. However, if you have, say, 6 system elements, and you draw your 6x6 n-squared chart, and you find that every single cell is occupied, and sometimes you've got 3 or 4 different interfaces in each cell, that is clearly very tightly coupled. If you look at best practice 6 or 7 of my list, if you can try and make as few entries as possible off your leading diagonal. The example I've given there and in the book is sort of daisy chain from system element 1 to system element 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, and then 6 to the outside world. For example, it's idealistic because it never quite works like that in practice. But if you try and get as few entries as possible, say 1 to 4, there's no interface. 1 to 5, 2 to 5, there's no interface. Then you're reducing the level of coupling. There is a danger that if you overdo it and you oversimplify, that you can introduce single points of failure, but that's architecting for you. Okay.
Perfect. And then a question from Jessica. So if you had one key message regarding interfaces that you wanted early career engineers to know and take into their work, what would it be?
It would be, for the bits that you're working on, if it is either a whole system or a system element, can you get all of the interested parties in a room and agree on a context diagram? Hazel used to say, and give an example. In fact, she did this last week in her basic principles tutorial for the international symposium. If you get 6 people in a room and ask them to draw a context diagram independently, you've got about 75% chance that they won't match. If you introduce a couple of the stakeholders from the systems with which it is supposed to interact, it's now up to about 95% certain that they won't match. So don't draw it yourself, draw it collectively, the whole team, all of the interested parties, and keep it on your project wall so that everybody knows what interfaces they're supposed to be worrying about. Okay.
Great, thank you. On a similar vein, are there any best practice or tips for planning verification activities for interfaces?
Okay. I'm just putting the finishing touches to the next Don't Panic book in the series on integration and testing, so watch this space. There is a bit in the book, the interfaces book, about how to do phased integration and the use of simulators and models for representing the system or system element at the other end of the interface that hasn't been implemented yet. Yeah, and you need to make sure when you're planning your integration strategy that somebody is responsible for, somebody who isn't the original designer is responsible for creating that model or simulation so that you can do your integration testing.
Perfect, thank you. Just to loop back to the previous question regarding Crossrail, Sanjeev said Crossrail failed due to interface failure between signaling and systems engineering disciplines.
Okay, I'm sufficiently out of the loop now that I can say that the single disciplines in UK rail industry just don't listen to systems engineering. And in particular, the signalling discipline is probably the best of the bunch. They tend to know what they're talking about. But It is very highly stovepiped, the UK rail industry. Signallers only talk to signallers, track engineers only talk to tracks, civils only talk to civils. And very often the cross-disciplinary interfaces between them are ignored.
So thank you very much, Paul,
Sorry,
for presenting.
Can I get Jessica to comment? She's put context diagram as the first thing I get people to do. Very unintimidating way to get people to engage. I'd like to hear about that if Jess can turn her mic on. Is that because when you're drawing that context diagram, you're effectively assigning responsibility for who does what across each interaction. Is that unintimidating? How well has that worked? I'd love to hear.
Hello, can you hear me? Because you're on my television, but I'm on my laptop.
Yeah.
Okay. Well, I think it's just, let's draw this one diagram together, and I tend to approach it very creatively. Everybody has an equal standing. I think in drawing it to begin with and getting people to engage that way, that's when it's very intimidating. But then you can use it for those difficult conversations later of, okay, now we actually have to assign some responsibility. But I think it's a very easy way to feel like they're involved and therefore have ownership over it as well. And I think that softens people as well when you start then talking about that responsibility. So in my experience, it's that's how it sort of work around it. So that's what I meant by it being unintimidating.
It's great for getting collective ownership of the joint responsibility.
Yes.
But is it comfortable for people who've never used them before? Is where I was going, I think.
Oh, okay. I think if you, I don't know, when I do this with teams, I'm always very involved. It's I will hold your hand through this. It's a safe space, like we're doing this together, and there's a lot of support there. And that seems to have worked well. That's
great. So, right. So moving forwards, fewer neglected orphans is the objective. Thank you all very much, everybody.